and considering the receiver is matched to an antenna where the noise figure, where the noise is going to be because of thermal noise. So assume that the power from noise is kT. It is Boltzmann constant, and T is the room temperature. You get the noise figure as minus 124 dBm per hertz. Substitute in the formula, you will get the power sensitivity, the minimum sensitivity for which the receiver has to be designed. So I am just calculating the value of PRS, assuming that the PRS is a thermal noise kT R into delta F. I assume R to be 1 ohm, delta F to be per bandwidth. So kT, K, you know, it is Boltzmann constant, and T is going to be the room temperature, 27 degrees Celsius, or in it is 290 Kelvin in Kelvin scale. And K, you know, it is the Boltzmann constant. So if you substitute both the things and take logarithm, you get this, and the first term can be replaced by this noise. So P sensitivity equal to minus 174 dBm per hertz plus noise figure plus 10 log B plus SNR minimum. So the first sum of the first three terms, the total noise of system, sometimes called as noise floor. So the first three terms, they contribute to what is called as noise floor, the minimum noise level above which your receiver is working. Because SNR is still there. If SNR is not there, this will be completely noise. Since SNR is there as the fourth term, the first three terms together, they are called as noise floor. So if you draw a line, if this is your noise floor, if you have a minimum SNR operating on the device, your device will be operating above the noise floor. This is a very good receiver. If your device is operating below the noise floor, then the noise is dominating, so the signal SNR will be 0. When SNR gets added to your system, it means that the device is operating above the